Hi all! Today we are going to be talking about CPU affinity. What is it? How does it affect your run? And how can you use the Survey Performance tool to help you determine your run's affinity, and how can you make your future runs more efficient? Survey is an HPC performance tool from all of us at Trends of Synergy. In the Survey report at the end of the run, Survey provides the affinity information collected at the beginning and at the end of the run. When the analyst report is selected, the NUMA domain information is also included, as well as some recommendations on the balancing of the MPI ranks and threads within the NUMA domain. This video is going to give a brief explanation of what affinity is and why the affinity and NUMA information included in the survey data can help you improve the performance of your HPC runs. Affinity is the map of how CPU cores are assigned to MPI tasks and OpenMP threads in HPC applications. HPC applications usually have a large problem to solve that is divided up into smaller problems and assigned to individual MPI tasks and/or MP threads. The HPC job scheduler, such as Slurm, assigns the cores to the job's MPI tasks. This can be affected by the run settings when starting the job. Sometimes the application itself will make further changes while the job is running. Affinity can have a huge impact on the run's performance because it affects how the node's resources are used. For example, if you have a run consisting of 4 MPI tasks and you are allocated 4 cores on a node, you would probably want to make sure that each task has exclusive access to one of those cores instead of having multiple MPI tasks sharing the same core while one of the cores is idle. Here is an example of the configuration of an HPC node. This system has 2 sockets. Each socket has 56 physical cores. Each core has 2 virtual cores, which are sometimes called logical cores. The cores of each socket are divided into NUMA domains, that is, memory resources, with 14 physical cores and 28 virtual cores per domain. Each NUMA domain has its own set of memory resources. If you have an MPI rank with, for example, 2 different threads, you would want to make sure that both threads are on the same NUMA domain. If the 2 threads of the rank span NUMA domains, and if the 2 threads pass data to each other, the performance of the run will be affected significantly. If the 2 threads are also assigned to different sockets, this will have an even worse effect on performance. If possible, each thread should also have its own physical core. If 2 threads are assigned to virtual cores that share a physical core, the threads will have to compete for the CPU resources. In a CPU-intensive application, this can have a significant impact on the performance of the run. If your node has multiple sockets, then you should try to balance the allocation of your ranks and threads evenly between the sockets in order to make the best use of the node resources. With each socket, it's also helpful to balance the allocation of rank and threads over the NUMA domains. In summary, when you receive your node allocation for your run, you will want to make sure that 1, if you have multiple threads per rank, those threads are assigned to cores that share a NUMA domain. 2, each thread should be assigned to its own physical core. And 3, your ranks and threads should be balanced across the sockets of each node. Within each socket, the ranks and threads should be balanced across the NUMA domains. Survey gathers affinity information at the beginning and the end of the run and includes that information in the report. If the affinity information does not change, it only reports one set of values. Now let's look at some examples of actual survey runs. Here's the affinity results from a run of hybrid Lulish run on a Cray system with an AMD node with 2 sockets, 64 cores per socket, 256 logical cores, and 8 NUMA domains. This run was performed using mostly default settings with a number of OpenMP threads set to 2. If you are using the bash shell, you can set the environmental variable using the command export omp numthreads equals 2. Alternately, you can add omp numthreads equals 2 just before the survey command on the command line. If you are using a different shell, your syntax may vary. So the 8192, that's just a Lulish setting. The -N64 means 64 ranks. And the MPI exec is what this particular machine used to start the MPI run. You can see right off the bat that these results are not ideal. Each rank has 2 threads, but only 1 core assigned to it. That means that for each of the 64 ranks, there's going to be 2 threads competing for the resources of a single core. If we look at the NUMA domain information, we can see that while there are 8 NUMA domains, our run is only using 4 of them. That means we are underutilizing the memory resources available on the node. Half of them are standing idle. Now let's look at the Affinity results after we updated our run settings. First, we set the environmental variable OMP places to cores in order to ask for 1 core per thread in our allocation. Believe it or not, this is not normally a default setting. We also set OMP proc bind to close in order to specify for threads to be allocated cores close to the cores allocated for the parent thread. Assuming child and parent threads often need to communicate with each other, this can improve performance. After consulting the man pages on the Cray machine we were using for the runs, we added --CPU bind equals core and --depth equals 2 to bind the MPI ranks to cores with 2 cores per rank in order to accommodate the 2 threads per rank used by our application. Your settings may vary depending on the type of MPI you are using and your scheduler settings. When we performed the run again with those settings, these were the new Affinity results. Now let me take a minute to explain the notation we use for Affinity results. We collect the Affinity data by looking for all ranks that were assigned cores or groups of cores. In the first line of our Affinity results, cores 0 and 1 were both assigned to rank 0. In particular, core 0 was assigned specifically to one of the threads of rank 0, and core 1 was assigned to the other thread of rank 0. We put both threads assigned to rank 0 on the same row separated by vertical lines instead of using separate rows, which would take up a lot more screen space. Notice the rank column is labeled as EQ rank number or equivalent rank number. That is because if you are performing a run with multiple nodes, typically each node will have the exact or almost the exact affinity. If you have a run with 2 nodes with 64 ranks for each node, and the first rank of the second node may be labeled as rank 64, but it behaves the same as rank 0 on the first node. Instead of displaying different affinity results for each node, we group affinity results together and renumber the ranks with equivalent rank numbers. The line that says nodes will list all the nodes with the same affinity results. Notice that the thread column is labeled as thread count instead of thread number. That is because sometimes 2 nodes will have almost the same affinity results, except 2 thread numbers may be switched. For example, on the first node, core 0 may be assigned to thread 0 and core 1 may be assigned to thread 1. But on the second node, core 1 may be assigned to thread 0 and core 0 may be assigned to thread 1. As long as both threads belong to the same rank and the NUMA domain is the same, this rarely has any impact on the performance of the application. So instead of denoting the actual thread number, we just report the number of threads that the cores were assigned to. This allows us to group the node affinity results that are almost but not quite the same. Now back to the affinity results of our example. Each thread of each rank now is assigned its own core. We are using all 8 NUMA domains, which is spreading out the memory requirements for the application to use all the node resources available. Now let's look at the effect of this change to the run's affinity on the performance results. To compare these results, we are going to use another survey tool called Survey Compare. Survey Compare creates a side-by-side HTML page that compares multiple survey results. To use Survey Compare on the command line, we separate the survey prefixes with a comma. You can add as many different survey runs as you want. I edited the fields that were displayed in this compare report by updating the config file used by Survey Compare. This allows us to focus on the data points most relevant for this comparison. As you can see, the affinity results have a really significant effect on the performance results of the hybrid Lulish application. The original run took about 10 times as long as the updated run with the new affinity settings. The instructions per cycle is a measurement of the efficiency of the CPU instructions. A bigger number is better, and our second run is about twice as good as our first run. The computational intensity is the same measurement, just inverted. You may be surprised to see that the affinity has any effect on the efficiency of the CPU counters. However, efficient use of the system resources may have ripple effects on the efficiency of seemingly unrelated performance measurements. The other thing to keep in mind about these results is that you are looking at the average results of each thread in the application. So these performance gains may be multiplied for the overall performance of the application, particularly for a large number of threads. Under our usage, these two values show the voluntary and involuntary software context switches. Although switching between hardware cores, as opposed to switching between software threads, may not always cause a large number of context switches, in this case our performance results show an enormous number of context switches in our first run with the poor affinity, and hardly any in our second run with the improved affinity. You can also see the performance improvements when looking at the measurements of MPI and OpenMP. Each of these measurements is significantly better in our second run. There's one final measurement to look at, and that is the figure of merit of the application. Some applications, including Lulish, include a figure of merit in the output of the results. This is a metric that is included within the application itself rather than a measurement performed by Survey. If Survey has a custom parser for the application, such as the parser we have for Lulish, we can parse the figure of merit from the output of the application and include it in the metadata. This FOM is not included in the compare report because the application data is different for each application, making it difficult to include in a generic template. But we can look in the metadata file for the run to find it. As you can see, the figure of merit is roughly 10 times as large for the good run as it is for the bad run. In this case, a large number is a good result. And that is consistent with our total time measurement results. Now, Lulish is only one application, and not all applications are as sensitive as Lulish is to the changes in the affinity settings, so your results may vary. But Survey is a really important tool that you can use to determine your affinity results, identify ways that it could use improvement, and then determine how much an effect those changes have on the performance of your application. I hope this video has given you some good information on affinity and how Survey can help you identify your affinity settings and how to improve your HPC run performance. If you like this video, please give it a like and consider subscribing to our channel. If you have any suggestions for future videos, please let us know in the comments below. Thanks so much.